Hi, welcome everybody. As I was saying on Teams, unfortunately, I'm not able to lecture live this week on campus. So yesterday was already at the video, and today is also as a video. So sorry about that. The video is still shooting in the library, so you can still notice a quiet please sign behind me. And today's objective is follow up what we've done yesterday, and also in a way, kind of like start to dig a little bit deeper into, well, we coded, we talked about planification, we talked about like slicing things, getting tasks, refactoring, adding new feature, getting a walking skeleton, getting this incremental iterative way, fine. But at some point, we can't do like anything anytime. We need to kind of like look at things and be sure that we have a concrete specification. We clearly know what we're doing, basically building a blueprint of what's happening. Interestingly, when you're doing classical engineering, building a blueprint is kind of like documentation of what you're going to build. But as we're doing software engineering, the code, that very blueprint, is actually also an engineering artifact, which in our case will be a module interface specification and an abstract data types. And that's what we're going to talk about today. And next week tutorial is really dedicated for you to practice that. This week tutorial is about slicing and planning, and next week is about formalizing specification in a way that you can action them when you're coding. So today, what we're going to talk about is first need, like trying to motivate this for module interface specification and abstract data types. Then we'll take an example of an abstract data type, and then we'll look at the maze example to kind of like see how we can do that on the maze generator. And as part of the tutorial, you will take examples on creating an MIS and not just an ADT. We'll get like MIS kind of like a little bit bigger than an ADT in a very, very coarse-grained way. So this lecture is based on two other lectures that are kind of like mixed together. First one by Zach Tatlock, and the second one by Jason Jascola. They're really good material. They're both available on Avenue. And also Dr. Spencer Smith, who was giving that course until 2 years ago, had amazing material and on MIS and AGT. And it's also available on Avenue if you want to kind of like dig further and get more about this. So first off, the need. Why do we need this? Because, well, usually classically, when we're trying to formalize a subpart of a system, we're going to create an interface. I'm not talking about graphical user interface or interaction with the user. I'm really talking about an interface. So this kind of like collection of method that can be exposed. So we have this. It exists in tons of different languages. If it doesn't exist, there's a way to have this. If you've programmed in C, you would have the header file, which is a way to describe like the procedural abstraction. There's a way to do this in JavaScript too. There's a way to do this in C#, in like tons of language support this notion of interfaces to kind of like capture what my things are doing. Not all, but still. So what's the problem with that? Like we have it in the language, we should use it instead of creating something new. So why can't we be minimalistic? I said a lot that computer scientists and software engineer in particular wants to be lazy. So why do I need something more than just interfaces for what I'm doing? Well, an interface, and there will be more on this later on the course, but just reminder of your object-oriented programming course, it's a cohesive collection of services. So you implement an interface, meaning that you're going to provide all the method described in the interface to the users of that class. Python doesn't have that. C neither. So it means that, okay, some language have, some language don't. So that can be a first motivation, like, oh, maybe I should not be weakened by my choice of language. If I need to define a module, if I need to define some things that's going to be reused, maybe I need to do it in a language independent way. And the second part, if you think, for example, of a header file in C or Java interface, it says nothing about the semantics. It gives you the signature. And the only semantics information that you might have is that, oh, all those methods comes together and it's packaged. You have all of those or none of those. but it doesn't say anything about how this method is actually behaving. And you don't have this in the interface. And basically why? It's because we're talking of a description more of a specification. A description, it's a key aspect. It's easier to understand, and it's actually not even complete. It's just like, okay, we're getting into the way of describing things. So it says what the product has as attributes, what the product can do, what this class can do. A specification is something more because describe the attributes required of a product. It's not saying like this is the way it is. It's if I'm satisfying that specification, then I do have those attributes. This is what I'm required to do. It's an abstract description. I don't care about how it's going to be implemented. I just care that I need to be able to do that. And this is how those things works. That might be very abstract to you. You might want to take a little bit of time to digest this. We can take an example. Consider those two classes. Both model a point. Coordinates, one is Cartesian, the other one is polar, but both are a point. Can I instantiate one class on an object from the class on the left and then use it as an object from the class on the right? Absolutely not, because there are different types. There are different ways of implementing what a point is. You see where I'm going to? This idea of, oh, there's an abstract description, abstract specification of what a point is, and using a Cartesian implementation or using a polar implementation, it's an implementation choice. It doesn't have anything to do with the fact that this is a point, and a point behave in a certain way. I can translate a point, I can create a line based on 2 points, I can blah, blah, blah. There's JTS, for example, is an entire geometric, algebraic geometry library that helps you to model polygons and compute on top of polygon and provides Cartesian and polar implementation. But at some point, I might have to choose, but both are points. So you get this need. I have a solution space, Cartesian, polar, which is way bigger than my problem space. My problem space is what the hell is a point? And it's something that I can translate, that I can add in a line, that I can add in a polygon. So those are the services that the point is rendering, is providing. But how it's done, this is not my problem. That should not be my problem at design time. It will be my problem at implementation time. I will have to code this in a way or another. But I really do need to get this as an abstraction. And you will hear me a lot in that course use the word abstraction because that's the key of software engineering. We've got the first technical key, the skill. Think of a walking skeleton, add the flesh on top of the bones, and iteratively and incrementally get to the product. But at some point, this assumes that we know what we're doing. And when we're adding a feature, we know what the feature is, what it needs, and stuff like that. So far, we kind of like put this under the rug, like, oh, sure, we know how to code, that's fine. Yeah, we need to kind of like be in between and look a little bit more about what we code, what do we need, why do we need this as part of our code. But we have tons of other lectures to dig into this. So what we're going to look for is really this notion of procedural and data abstraction. I'm not interested into how you're going to implement things. I know you know how to code. That's fine. And even if you're not comfortable with coding so far, you're going to improve. It's going to go, maybe sometimes it's going to take a little bit more time, but that's fine. You're going to be, everything's going to be fine in terms of coding skills. What's hard is finding like building the right thing, building the thing right. In that case, we're on the building the thing right part. We need to find the right method. We need to find the right objects. We need to find data exposition so that we developed software which is maintainable over time. So we're going to look for procedural abstraction and data abstraction, that the two dimensions that are really important, and that basically the two dimensions we're working on, because an object, it's procedure plus data, method plus instant variable that brings you to what an object is. So when we're talking about procedural abstraction, we want to be abstract from details of the procedure, methods, function, whatever you call it. It's really specifying this, what's What do I need? What's my signature? What the behavior? What the semantics? And then I can implement something that does the job. But first, I've thought of, okay, this is what I need, and this is why it's needed here. Same for the data. We need to abstract what we need from what we implement. A point is needed because I need to translate it, I need to move it, I need to add it in the line. The fact that it's a polar or a Cartesian one, I don't care. And in that case, what we're looking for is named an abstract data type. So data type, Cartesian point, polar point, abstract data type, point. Okay? And we can actually obtain, in that case, a global, what's a 2D point? If we consider everything that we can know, well, it exists in the plane, so it offers X, Y, R, theta. If I want to like provide everything in the same concept, I can create it, I can translate it, I can scale it, I can rotate it, like things can happen. So I'll have what's called observers, which are like a way to access the data. If we're talking in terms of Java, that would be getters. I will have creators, producers, that are method that creates a point, constructor, or method that gives you another point. Like if I want to take the centroid of a polygon, I'm going to take like all the points and it's going to compute the centroid. Or I can also have mutators that can be setter, or that can be anything that change the internal state of my object, okay? So when we have this, observer, creator, producer, mutators, we're going towards an ADT. But the point here is that I've never told you how the centroid computation work. I've never told you how the translation work. I've never told you how the scale and rotate work, like all those kind of things. I don't care now. I'm just expressing what my object is capable of. That's the concept of abstract data type. So how does it work? It works as a shield. The whole point here is really to get this idea of, I don't want to know the details. The rest of the programs, which are called the clients, the person that are calling my API, application programming interface, that are calling that abstract data type, they don't need to know the details. Worst, what would happen if they need? Put a video on pause for like 2 minutes and try to think of what would be the problem if I was exposing everything. Well, if you do that, if you give access to everything to anyone, you're going to get an entangled way of coding where everything is accessed from everywhere. And that's actually something which is wrong, which is named spaghetti code. You can imagine like a plate of spaghetti, and that's the thing that we will have in your code. Not maintainable at all. Maintenance hell, actually. So we need to protect ourselves. We need to find a way to be like, this must not happen. You're going to use only what I'm exposing and what I'm allowing you to use. If you want to use something else, that's just not possible. Deal with it. I'm taking a design decision here as software engineer that to interact with the point, you will interact with my modifiers, my constructors, and my observers. That's it. And by doing this, that gives me flexibility. I can change my mind. I can decide later on to totally replace my current implementation by a totally different way. Remember what we've done yesterday in the counting the points in tennis? Exactly the same. We introduced an interface, an abstraction shield, to be able to not be tied to something. We had this interface that prevents us to use something that is not exposed in the interface so that we can have flexibility. If I want to change the way I'm counting point at tennis, bam, I'm just implementing a new interface and instantiating a new object. That's it. The rest of my program is exactly the same. As soon as I follow the same specification, that all the methods implement the same behavior, the same semantics, sorry, how they're doing it, their behavior, that is not my problem. What is amazing with things that are not my problem? They're not my problem. So I can be lazy and assume they're good. Getting this assumption, it's really about delegating, organizing work. You can, if you're in a group of 3 students or in a bigger team working on a project in industrial context, you can define an interface and you can use this to kind of like say, okay, this is the things that we're going to call on you. Give us like a fake object so far, fake implementation that just always returns the same values. Fine, we're going to use this for testing. Work on your real thing. When you have the real thing, we just flip it. And we use a new implementation. That's called a mock object. And that's basically how you can design large scale stuff. But that's, you have like design 3 cores to work on this. But the essential point here is really this notion of abstraction barrier. We really want to prevent users, because users are monkeys. They're going to use everything they want in the way you've never thought about. So the better we engineer, the more we hide, the more we encapsulate. Tons of lectures coming on information hiding, information encapsulation. That's going to help us to be sure that the code is not hell. And this is really specific, considering this notion of ADT. So abstract data type comes with object plus operation, and all the rest is hidden. We don't want to expose anything but the specification, so that they can't know the details. If they can't know the detail, they can't use the details. So they can't be coupled to this, giving us the most flexibility we can have. There's different way of representing an ADT. We can do it in a mutable way, or we can do it in an immutable way. Usually you're used to the one on the right-hand side, the mutable, because basically that's what you've done with objects. Okay, you create the object, they have instance variable, and then you have methods that change their states. But you've also used immutable things. Let's, for example, think of the string class in Java. Each time you're creating a string, or each time you're having string A plus string B, what's actually happening is that it creates a new one that contains A and B. Okay, so you're not modifying the first one, you're already creating a new object. So at the end of the day, there are 3 objects in memory instead of 2. This immutability has tons of advantage, but also some inconvenience. We'll discuss this later in some examples, but at some point you can ask yourself, if this thing's gonna move, if this thing's gonna change, can I make it in a way that's not changing? If I can, I'm helping the compiler, because the compiler can run some optimization on this, because the compiler knows that these things will never change. In Java, you can use this with the notion of record, for example. When something is not going to change, just a data class, just state that it's a record and it's going to be immutable. And you can also use the notion of declaring stuff final. When you say that something is final, it means that it's going to be that value and nothing else. So that also gives information to the compiler, and the compiler can kind of like do things better and make your code more efficient at the end of the day. So of course, if you have an immutable object, there's no mutator. And if you have a mutable object, the notion of producer is pretty rare, because usually you're just modifying your object, you're not creating new objects. That being said, if you consider, for example, the centroid method that we had in the previous slide, that's kind of like a producer, because I'm taking a set of points, a collection of points, and I'm producing a new point, which is a centroid of those ones. Okay? So second point, representation invariance, and to do this, we're going to use a polynom. If we were doing, let's say, air quotes, real engineering, we'd have models of bridges, models of material. We'd know that that's construction can hold up to a given number of tons, and if not, it's going to collapse, all those kind of things. We have some stuff that are invariants. Why? Basically because, well, the laws of physics. You can't go against gravity. That's pretty tough, but still, that's right. It's a law of nature. In software, if suddenly I want to go against gravity, I will just invert gravity in my code, and suddenly I'm going against gravity. So we have way more flexibility. Remember, when you just take like the number of version of Linux you can build, it's more than the number of atoms in the visible universe. So we are handling and managing really, really big objects and object space, sorry. As such, we need rails. We need stuff that prevents us to go off track. As such, we need to, in a way, kind of like look at what we're doing and take a step back. Because if I stay at the code level, fine, I can code whatever the hell I want. It's going to be fine. But might have problems, might have bug, and I can't know where it comes from. So finding a way so that this is always true. This should always be true. This is a precondition of my method. This is a postcondition of my method. This gives me information about the contract I have that helps me adding semantics to what I'm doing. So let's take a polynomial, okay? We take this notion, and a polynomial is what is C0 plus C1x plus C1x squared plus blah, 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 okay? So I'm basically defining an abstract state. I'm not giving the value of C0, C1, C2. I'm not giving the value of any of those coefficients. I'm just saying that, well, I have the definition of a polynomial. In that case, what I'm saying that it's immutable and it has integer coefficients. So I'm kind of like creating an abstract model of what a polynomial is. Important point here, this is abstract, it's specification. Also important here, you're realizing that this work we're doing on ADT and later on MIS, this is documentation. In that case, it's pure Java doc. Okay, or it can be, we're going to use an MIS template in a tutorial or in your assignment, but you got the point. This is documentation. We're documenting the project precisely where we need it. This is a critical part. I need to know what I'm doing. And as such, I'm going to take a step back and I'm going to describe the semantics of what's happening and specify what's happening. I can find the creators saying, oh, to create a new polynomial. In that case, it's a constructor that takes nothing and it has an invariant. That's an effect, which is the polynomial that is created that way contains no value, no coefficient. And I can build something which is instantiating an arbitrary unique polynomial, which is poly Cn, which is I'm going to create C times x by the power of n. Okay, so that's a way to build a polynomial. And it has some effects, which is creating the stuff. It also has some exceptional behavior. Like, oh, if you give me a negative exponent, it's not the case. This is not what I'm doing. Well, because based on my specification, all my coefficient goes increasing and I can't go negative. That's important because there was nothing in the initial description that was really saying this. It could have had something which could be negative, maybe. Maybe there's a definition of polynomial that would accept this. Being able to specify this, that's also a way to be sure that I know what I'm doing and I can actually express test cases. More on test later, but in that case, it means that if I'm creating a polynomial with a negative value, I should get an exception. Because if not, I'm not respecting specification. And people will assume that my specification is right. People will assume that they can't do that. So if they do it, that should be an error. And I will also provide observer being degree in that case and coefficient to get like the x coefficient of something. Again, that can create, that can throws exception. And you see the whole point of I'm basically describing the specification of each method. I'm not telling you what the implementation is. I'm not telling you how you're going to implement it. I'm just telling you that if you call degree, this is what's going to happen. How I'm doing it, trust me. I'm providing an implementation that respects that specification. That gives you two things. One thing is trust. You know that when you use an object, which is an instance of poly, well, if you call degrees, this is what's going to happen. Second point, that gives you, so that's when you're the caller. If you're the writer, the creator of this, that gives you a very important stuff, which is what do you need to test? What are the corner cases that are important that you need to verify before providing your code to others? Oh, for the coef, I need to check if the parameter is below 0, because if it's less than 0, I should throw an exception. So I can write a test case to do that. And finally, if we look still on the observer, what you've classically designed in object-oriented programming course is getters. Each time you get an instance variable, you do a getter, you do a setter. That's actually bad design, and we're talking about software design here. Do we need that getter? Is it really important to expose this? If we need it, then fine. If we don't need it, encapsulate, hide. The more you hide, the better it is. And also, we'll see in next lecture next week that can create leaks. If I'm providing a getter to something and then these things can be modified from the outside, that can have I can have problem later on. So in that case, if you look at this, I've never told you what my instance variable are. Never told you how I was going to implement the coefficient. Never tell you that. What I'm telling you is that you want the coef, call coef. You want the degree, call degree. And that's it. How I'm doing it, not your problem, mine. So that's really important, and that's something you have to keep in mind. Getter, setter are not systematic. You're going to hear me say that a lot during the course. You need to have observers that actually provide the right level of service. I need to observe this. I need to have access to that information. That information can be an instance variable. That information can be computed from other instance variable, but I don't necessarily need to have a getter and a setter for each and every instance variable that I have, because that's basically against the notion of information hiding, having this abstraction shield that actually prevent others to know the details. What we also have, so if we look at this notion of producer, in that case, we've made the polynomial immutable. So we need a way to assemble, to compose the polynomials together. And in that case, I can add a polynomial to another one. I can multiply a polynomial by another polynomial. I can negate a polynomial. I can have like atomic operation that creates new polynomial based on the given semantics. And that semantics is actually described in the comments. It returns this plus q. It returns the polynomial equals to this times q. What the definition of plus, what the definition of q, it's mathematics, it's algebra actually. So I can go to this definition and say that, okay, this is a plus. So there's no point into documenting by getting like the whole mathematics and algebraic description of what adding a polynomial means. It's here the point that to say we're using that notion and this is part of like domain knowledge. So this is what we're doing. We have the right amount of information. If I want to understand what the add method do, I can look at that and say, okay, this is how it is. It's the addition between two polynomials. I can go to Wikipedia or whatever, Algebra 101 book to get this. And we basically get the right understanding of what's happening. But again, I never told you how this is going to be implemented because I don't want you to know. If you're calling me, trust me, I'm going to do it on your behalf. And that's an essential point in object-oriented design. You're delegating to another object. I don't know how to add polynomials. You know. So I'm trusting you, and I'm just calling the right method. Do your job according to the semantics that is part of your abstract data type or your MIS. Give me the results. How you do it, I don't know. I don't care. And another point with the notion of producer is really this, that you should be very careful when you program that, not because it's hard, but it's because you're not used to doing it that way. So sometimes you might actually produce something, but also you had a side effect on your own object and you've modified it. So be really sure when you're going into this idea of immutable, because again, that will help you save memory, that will help you make code more efficient, that, well, if it's immutable, it's immutable. It's not going to change. And I can guarantee I need to be careful that it's not going to change. Back to the string system and the string implementation in Java, why it's immutable, it's very interesting, but it's all related to memory management. And the whole thing is that when you write code, which is string plus string plus string plus string, this is actually terribly inefficient. And there's classes in Java to do that. For example, a string buffer that's going to help you append elements. And at the end, you can flush the string buffer, and that creates the right string. So you instantiate once and for all, one big string, instead of having to get one, get the second one, create the third one, get the fourth one, create the fifth one, and going each time by creating new objects. So far, what we've done was really to motivate the idea of we need those documentation, we need to understand what's happening. What we do need to do now is basically see, okay, we've seen this polynomial example. How do we do that? So we're going to take maze example because it's kind of like a running example in that course. So we're going to be a little bit bigger than what we have. And actually, this course is just the opening of next week's tutorial. It's now because you need to think of what you're doing. So you need to keep in mind, and that was yesterday's demo too, that, oh, we need those abstraction shield. We need to be careful when we're creating something to be sure that what we're doing is doing it in the right way. Next week tutorial will be, okay, we take a simple problem and we get through a method to extract those. And you're going to do it with your TA, and then you're going to apply it to your assignment by working on that part that requires an MIS in the assignment description. So tutorial next week is here to help, designed for you to practice this before practicing it in your assignments. I use this section and the 20 remaining minutes-ish, might be less than 20 minutes actually, but still, to see also how we can came back to the UML and kind of like get an understanding of that graphical language. So this is a class diagram of the walking skeleton we obtained at the end of lecture number 3 when I was giving you the demo before running to catch my plane, actually. So one point is also the motivation for you to, why do we need those? Well, it's way easier to get a comprehensive vision of the maze generator by using this picture than by going to the repository and going class by classes, okay? What it's saying is basically saying that I have a configuration which is immutable. Configuration contains the width, the height, the seed to the random generation, the output file, those kind of things. I can load my configuration. I have a main method. That main method contains a maze exporter, and I have access to a maze. This is how I can create a maze, and this is how I can carve a maze. Okay. So what we have so far is kind of like this global representation. There are some hints in the way UML works. So each box is a class, which is one thing. Each arrow here is a reference. So that reference means that the main class knows the configuration class, the main class knows the maze exporter, the main class knows the maze. And there's also something interesting here. Those two methods, they're basically stating that the load method and the main method, they're static. So those are the two only methods that are static. All the rest, they're object-oriented methods. Second point, I'm also giving information to you guys in this about how to create. So to create, I'm calling, this is in UML classically called a this, which is new in Java. And I have a constructor that take a maze. I have another constructor for the maze that take a width and an height. Might require a little bit more practice for you to be able to map this from code, but this is what we're going to do again, example after example. If you're not 100% comfortable so far, that's fine. But you will see, for example, in that slide, kind of like mapping both. So the maze class, on the left-hand side, pure Java, on the right-hand side, pure UML, it's basically my walking skeleton. And what I'm saying here is that I have my maze, I have a constructor, and I have the method to carve. Which is interesting here is that I have exported two methods here that are not actually part of the model so far. Why? Because so far there is no need to kind of like make it available. The need is that I need to expose a constructor, I need to expose a carving. Those two, I'm not sure if I need them. And actually, I just need them because so far, all mazes have the same size, which is 41 by 41. So it's just a way to get this. But you see, it's not even linked to anything. This is technical debt. First, I don't know if I need those. And second point, this is not implemented the right way. So that can be a problem. But you see, so class maze, this is a public maze int with int 8, which gives me the this, with is an integer, ace is an integer, and that gives me the carve that take a random. That gives me the carve that take a random. Those two, they're implementation details. I'm getting rid of them in the model. My UML model is not a 100% accurate reflection of the code. It's an abstract description of what I need to know with respect to my code. What I'm exposing here is that a maze, this is how you create it, this is how you carve it. End of story. The main point here is that this graphical structural representation is not enough. I have absolutely no information about how to carve a maze. I have no understanding of how actually carving exporting works. And worse, sorry, if I look at, so in that case, this is named a sequence diagram. Each lifeline represents an object. and each others represent the creation of an object. So here I have this kind of like main class that is creating a configuration, loading the configuration, then creating a random generator, creating a maze, carving the maze, and exporting to the maze. So I have like one element that is sending orders to all the others. So it's really like a central way of defining this, and that's actually not a really good object-oriented way. It's really highly coupled to everything. More on this later. We're gonna like decompose this next week, but just to show you how you can represent the behavior of your system. Okay, so if you remember the demo, that's what we had. We first load, then we get the random, then we get the maze, we carve it, we export, and first we instantiate the exporter and we get the exportation. Each time there's an arrow that goes from this to this, it means that the main is actually calling this. So the main method is actually calling carve, sending a carve message. So that's the object-oriented vocabulary. We're sending messages to other objects. And then the maze is busy, does something. That's what this box here represents, and then returns something. And my main was busy the whole time because my main was doing everything. Okay? So the problem we have here is that if I just take this, I have no idea how to carve. I have no idea what the contract is. I don't know what to do. You've done some stuff. We have a working skeleton. Fine, but you're not helping me in any way about how do we carve this actually. So there's two options. And you can take like put that video on pause and try to think of the problem before moving to the next slide. So option A, the problem that the prophet is evil and he's giving only vague and imprecise tasks to mess up with your head and make you spend an infinite amount of time on this shitty course. That's one thing. Second option, that the prophet is evil, but software engineering is even more evil. And it's part of the job to turn an imprecise and vague description into actionable artifact. Because what we have so far, it's a walking skeleton. It's kind of like Java. It's kind of like close to the machine, but still it's imprecise. It's very vague. We don't really know how to carve a maze. So unfortunately for you, the answer is B. So yes, I might be evil, who knows? But yeah, software is vague. That's part of the deal. What does carving a maze means? What does instantiating a maze mean? I have no idea. I have absolutely no freaking idea how it works concretely. So I can be totally terrified and paralyzed by the fact that, oh, there are so many things I don't know. I can't do anything. Or I can apply software engineering approach, which is, okay, take a deep breath. This is what we need. Let's describe what we need, not how we do it, just what I need. And then I will get my structure. When I have my structure, I can go deeper and I can actually figure out how to carve a maze using any super fancy algorithm that can be used to do such task. Okay? Small, tiny steps, decomposing the problem into something that I can manage with a reasonable amount of stress. To do this, we're gonna like pimp up a little bit the notion of abstract data type, and we're gonna go for what's called module interface specification, MIS. In that case, it's just like ADT on steroids. So we want to describe the externally observable behavior of what's happening. So no information about the insides, like an ADT, really nothing, just what we have. And this goes, in the tutorial, you'll have a template of the things, and we'll go through a method to fill out the template. But it's basically like the name of my module, what's a maze, the other modules that are imported, maybe a maze use something different. If the maze use graph theory, maybe it's going to import a graph module that provides some services. The MIS also describe the interface, so the method signature, the exception, the types that are exposed, the constant if they're so. We'll give some invariant. Remember in the polynomial, we had some invariant representation, coefficient can't be negative, stuff like this. This is something that needs to be exposed and described. We'll give the state variable. How can I move from one state to the other? What it means to call a method that moves from one state to the others. How do I start? What are my initial values? And also will give me the behavioral rules, like if I'm in that state, I'm moving to that state through that method, this is what's going to happen. Again, not describing anything about implementation and how those things are done. It's really all about what I need and what the semantics of what I need. So let's look at the maze. What do I need? Well, I need an initial state. When I'm creating a maze, there's something. Oh, but the maze, it's tiles. So I need to decide what I do with the tiles. So I'm going to decide that my maze is a rectangle width times 8. Okay, that looks pretty decent. And that maze will be full of walls. That becomes interesting because that gives me like a chain of thoughts. What the hell is a wall? Like, well, that's a kind of tile. I said my maze is a set of tiles, is a like matrix of tiles. Gives me another thing to thought of. Okay, so if a tile can be a wall, can be something else. Yeah, that can be a path, that can be empty. So that gives me the description that, oh, actually, my maze has an initial state of matrix width times 8, full of walls, and a tile can be empty or can be a wall. And then I have some more behavior. Okay, I want to carve a path. Fine. There's a precondition. The maze exists. And based on my initial state, I can assume that whatever the maze I receive, if I'm asked to carve something, the maze I'm going to receive will be full of walls. It's part of the contract. There's no way to guarantee this in Java, Python, C, C Sharp, whatever. I can't force you to instantiate an object in a given way. But what I'm telling you is that, hey, dude, if you're implementing my description, my specification of a maze, this is what I'm expecting you. That's a contract. You have to respect my contracts. And the post condition is that there's an entry point, there's an exit point, and there's a path guaranteed that goes from the entry to the exit. And you could be like, okay, that's common sense. Fine. But what's an entry point? What's an exit point? If you look at the maze generator, there's something more in the specification, which is, oh, the entry is always on one side and the exit is always on the opposite side, and it's left, right. Never we're going to enter by the top or exit by the bottom or the other way around. It's always left to right to left, and that's it. But you see the chain of thoughts, you see the process that is behind. I'm starting with something simple, incomplete, coarse grain, not perfect, fine. It's not a failure, but it's still incomplete, but I have it. A maze is a rectangle, width times a's, full of wall. And when I have this, I can refine and say, okay, a wall, oh, that can also be empty. And what does carving mean? Going from exit to entry to exit. What's an entry? What's an exit? What are the precondition, post-condition? And I can more and more refine to get a way more complete specification of what I need to do. And what's amazing is when I know what to do, programming it is usually not that complex because the complex task was decomposing and finding the right way to find the right method, the right post condition, the right invariant at some point on this is how it needs to be. And when I have this, coding it, well, I can code it. I can write test case that check my code is great, and that's fine. And then I have kind of like peace of mind through my initial investment, which was what the hell do I need to do so that I can code it later on. So if you rinse and repeat that process, we'd end up with that description of the maze on the right-hand side. What's interesting here is that there's different way of carving a maze. So if I want to protect myself from that, I'm going to create an abstraction shield, which is a maze carver, because I don't want to be tied to a given way of implementing. So a maze carver just tell you, okay, you can carve a given maze with a given random generator. And I'm going to provide one instantiation of this, one implementation of the maze carver, which is the one that uses Prim's algorithm. There's others, crucial algorithm, balance equilibrium algorithm. They're not top of my head right now, but you got the point. So anything that respect that interface can be used in my code. Totally fine. I'm going to give some accessors, observers, tile at given location. For a given location, give me the neighbor. I have in a maze, tell me for the Y and X position, which kind of tile. Which kind of tile? It's an enumeration of being empty or being a wall. So you see, my questioning that I was having on the previous slide, which was just like, okay, chain of thoughts, what's happening? What is this? What is this? Just describing, being precise for the things I was talking about, that's translate into a model. And we've seen in the previous slide that this model, this UML model, can translate into code. So it's kind of like a continuum. I have a spectrum from this pure documentation to the model and then to the code. And the main point here is that at the model level, just at that time, when I'm specifying this module interface specification, when I'm specifying ADTs, depending on the level of abstraction that I'm looking for, I don't know. And I don't care how the maze work. Is a maze stored in a matrix? Is a maze stored in a list? Is a maze stored in a hash map? Is a maze stored in a very super fancy graph theory algorithm, whatever graph theory structure? I don't know. I don't care. That's not my problem. It's an internal choice. And by doing this, by having this representation, which is this is how you're going to use a maze, this is how you're going to carve a maze, this is how you're going to represent a location. I'm just showing you some abstraction, and I can do whatever the hell I want behind this. I can implement the maze carver. I can implement the maze the way I want, basically because I've never exposed to you how I'm doing it. And you're doing it all the time. You're using it all the time. When you're calling a method from Java, you're instantiating a hash map, you're instantiating a linked list, you're accessing elements in an array. You have no idea how it works. But this is just code. So you're just consuming something. And now your work is to be able to provide things to others because, well, you're not just consumers anymore. You're a producer. You're producing code that's going to be used by others because your code is maintainable over time. Got the point? That brings me to the conclusion. And the conclusion is like, sure, we can code is the truth. We need working skeletons. We need code that works, but that's build the right thing. To build the thing to build the thing in the right way, we need to specify. We need to know that we're not just writing code and dumping code so that, well, we have it and it's crappy, it's full of technical debt, and no one wants to maintain that crap over time. No, that's not what we want. We need blueprints. We need elements that will allow us to be sure that we're not doing nonsense. And by working on this, getting the description, getting the specification, getting invariant description that think this needs to always be true. This is an assumption that you can make if you're calling my code, if you're calling my method. This is what I guarantee to you. That gives you really trust and peace of mind. I'm calling this, that's fine. Everything's fine. This is what they're going to do. How they're doing it, not my problem. And finally, in the maze example, you'll see that just a data structure that would be, okay, a maze is an array of tile. This is not an MIS because I'm not explaining you anything. I'm not explaining you how to observe. I'm not explaining you how to produce. I'm not giving you the initial state. I'm not giving you the precondition of my carving method, all those kind of things. This would be totally non-covered. And that's really important. Getting an MIS, it's obviously what you need. In that case, I want to understand the maze because the maze is so critical in my system that I really clearly need to get its description and more, its specification. So of course, we're not going to create an MIS for each and every part of the system. That would be way too much documentation, and that actually might be loss of time. What we need to create is actually identifying the critical part and specifying those ones. This is critical. We need to get a global understanding of what's happening there. When we have this, we can go into implementation and we can check that the implementation respects that abstract contract. Thank you very much. That ended up being only 49 minutes, which is great. I was expecting less, honestly, but took my time. If you have any question, I'm going to say it on Teams again, like for the lectures from yesterday, use Teams. There's a post on Teams for Q&A. As Q&A, my internet access is kind of like unstable, but I can still answer the question. I will answer your question. Just formulate them in writing and you will get answer on this. And when you're posting question, if you can precise like which slide you're referring to, that like which number, that would be pretty helpful. So I can like point it out, like for yesterday's demo. Thank you very much, guys. Enjoy your day and see you on Friday for a real lecture that time. Bye.